Last week we finished up with the nervous system by covering the remainder of the spinal cord, and we started with senses with talking about the visual pathway as well as some of the structure of the eye. This week we are going to finish up senses, and we have a little bit more of the eye to talk about, but we're going to move on to go over the different senses, both anatomy and physiology. And then next week we're going to move on to circulatory system, including blood. Now, as we introduced this distance learning scenario, we were spreading things out, but with our course, I'm sure you're well aware, we have a lot of content to get through. My goal is to do a unit a week now. At this rate, I know that's a lot of work for you. It's a lot of work for me too. However, I really just want to make sure that you're exposed to this content before you move on to college. So while we might not get in depth as I would like to, just to accommodate for the amount of time we have, I at least want you to have that background knowledge that is going to benefit you come post-secondary ed, meaning whatever you continue to move on to. Okay. The other thing is with our notes, I had been doing more of an outline layout. I know we all take notes differently, but also the outline can be a little more time consuming as you are trying to go step by step to help us with the amount of time. And also because I know we each have our own organizational style, I've decided to move to showing the diagram and then having an additional note section on the bottom of that page. That way, I've covered whatever's in the slides. If I've said anything that you want to add, though, that can go in the additional notes. And then the last change I made in the PDF fillable with the labels. Yes, the labels are kind of small, but the PDF document will let you do a scrolling text. So while you fill in the label with the anatomy, it will actually scroll those words over so that you can continue to type even if there's not space. So that means that in each text box, you can actually put the label and the physiology for each component and keep the physiology right with the anatomy. And so when you click back on it, you can see everything that you typed in that box. And I think that's a great feature that you could benefit from. All right, let's get into senses so we can wrap up the nervous system. Okay. Also, if you hear Buford during this video because he's snoring, I apologize. He's currently asleep under my desk. Oh, the life. Okay. So we should be familiar with what the senses are: vision, touch, taste. Taste is also called gustation. Smell, which is olfaction. And then hearing, I've combined, I know I've added balance. That's not technically one of your senses that, you talk about. But balance occurs in the ear. And so when we go to talk about hearing, I think it's important that we distinguish between the features of the ear that focus on hearing versus those that focus on equilibrium. Okay. This image here should not be new to you. We had this last week. And I bring this back up because I want to chat with you about the cow eye dissection that I sent a link out. You should have watched that. A couple of things that are similar with our own eye. If you noticed when the gentleman was cutting through the sclera is the white of your eye. It's very thick. Ours are thick as well. Probably not as thick as a cow eye, but still pretty thick. And then We have that choroid layer, which is very dark. It prevents the scattering of light. And then we have the retina, which is where our visual neurons are going to be and our visual receptors. The other thing that might have been very noticeable in the dissection is when he cut into it, the liquid was actually pretty gel-like. And that's really what the vitreous humor is like. The vitreous humor is the fluid that's in the back or the posterior chamber of the eye, and it has a much thicker consistency than the chamber in the front of the eye, which has aqueous humor, which is more water-like. And then the fovea centralis is the area where our main vision is focused upon. Everything outside of that fovea is going to be our peripheral vision. And so with this fovea here, you have light entering, you go through the cornea, it's reflected through the lens, and it hits onto the fovea. The lens is going to focus that light so that it can then trigger a response. So let's take a look at that response real quick. We've already talked about this. Again, this is just review. Pathway of light is going to hit the retina, travel through these layers here. It's going to come in contact with the choroid. The choroid's going to prevent the scattering of light. From there, if that light is high enough to surpass the threshold, we will have depolarization. That depolarization will then lead to the impulse traveling through these neurons here to the ganglions or to the the ganglions, and then to the optic nerve. Once that depolarization is occurring through the optic nerve, we're going to have a bit of sharing of information here. Half of the information from the right eye is going to be shared with the left side of the brain and vice versa through the optic chiasma. And that's because when it comes to your vision, each lobe is interpreted by the opposite side. And so, as you can see here, we're looking at this fixation point that is a combination of the left and right eyes. Okay, so we need to share that information so that when only the left eye information is coming in, both my left and right occipital lobes are able to interpret. By having both sides interpreting and receiving information from both sides, that's how we can get our depth of field so that you know how far to reach for something or how far something is away. And it also kind of puts perspective on your vision. Where exactly is something sitting regarding its orientation to where your body is? Okay, so it's actually quite common if somebody has an injury to one of their eyes, they have to readjust to what's known as proprioception, or the movement of your body, the coordination of your body, because if they go to say pick up something, they might accidentally be a little far to the left or a little too close to their body, and they have to learn to adjust and accommodate for that lack of information on the other eye. Now, this is the anterior surface of the eye. Here is where we are getting into new content. You will see on your notes that I've given you the diagram. You have the text boxes so that you can label. And I highly recommend that as you're labeling, you're filling in the physiology for these structures. Okay? Let's go ahead. Just like I kind of did in class, I'm not going in order. I am going to be jumping around these labels a little bit, so just be mindful of that. So first off, basic structure, upper eyelid, lower eyelid, right? Here you have somatic control of these areas, so you can blink, can wink, right? This is protection because you can help cover the cornea, prevent damage, but then also this is going to help with relubrication of the eye. We're going to talk about that in a second. You have the lateral commissure, which I'm going to highlight here. The commissure is this corner here of your eye. If this is the lateral side, we're also going to have a medial commissure right here. The sclera, as I mentioned earlier, is the whites of your eye. This is pretty thick. The iris is the pigmented portion of your eye. And the pupil is the hole in the iris that allows light to enter and pass through to the retina. The pupil is adjusted based on the amount of light that you need let in, as well as the amount of focus. So it's just like a camera lens. If you need more light, the pupils dilate. If there's too much light, they will constrict. And a more narrow pupil means more finer focus. A wider pupil is going to be shallow focus. All right, let's get into physiology now. You have this gland just above the lateral commissure called the lacrimal gland. The lacrimal gland is going to produce an aqueous solution, in other words, your tears, and it's going to be released just at this upper eyelid area here and near this lateral commissure. With that, your eye's movement and blinking is going to help spread that aqueous solution across the eye and keep the eye lubricated, because you've probably experienced it. It's very uncomfortable when your eyes are dry. So having that lubrication makes it easier to look in different directions, to blink. It's just more comfortable. The caruncle is this little cushion on the other end, and it's kind of like a landing pad for the aqueous solution. So we are going from the lacrimal gland and we're glossing over the eye and then hitting the caruncle. That's the little puffy inside corner where sleepies, if you're making fun of me for saying sleepies, that's not nice. Some people call them eye boogers. I call them sleepies, but that's where you get sleepies stuck in your eye, in the caruncle. And when that fluid hits the caruncle, it's then going to start to drain through the lacrimal canals. You have a superior and inferior portion. You can see the opening of these canals if you really look in your eye. You've probably already noticed them. These lacrimal canals are going to drain here where they merge into the nasolacrimal duct. Normally, we have a general amount of fluid that this duct can maintain. In other words, the amount of fluid that's crossing our eyes does not overwhelm the nasolacrimal duct. It can likely evaporate or be reabsorbed into the mucous membranes. However, there are instances where it becomes a little more difficult to maintain if there's too much fluid. A couple of examples here. So here's our nasolacrimal duct, and normally the water can hit the nasal cavity or those tears and we'll have evaporation. If you're crying, you're going to have an excess amount of tears flooding these canals, which is then going to flood the nasal cavity and cause your nose to run. Just like spicy foods. Spicy foods can result in the excess production of tears. Those tears flood the canals. It then is too much to be evaporated and it's no longer absorbed. It is just gushing via mucus. So that's why your nose runs when you have excess tears. think I've covered everything that I want to cover about this diagram, so let's move on. We're only going to talk about touch very briefly. Back in the beginning of the year, I gave you some information about the integumentary system. I did a video on the integumentary system, and that included this cross-section of anatomy. So really, in this image, I want to focus on, yes, there's some anatomy, but I really want to focus on the physiology of certain regions. To start off, hopefully we are familiar that our skin can be divided into the epidermis and the dermis. The epidermis actually has 7 different layers. The dermis only has 2, but that, if you need a refresher on that, you can go back and look at my integumentary video. I want to highlight epidermis and dermis just so that you know where at these certain features are. Some that are more superficial are going to be found in the epidermis. Those that are deeper are going to be found in the dermis. The first is a mechanoreceptor called a Meissner's corpuscle. Meissner is the name of the gentleman that discovered these mechanoreceptors. And Meissner corpuscles are in the epidermis and responsible for fine touch. Okay. Think about where you're grasping or manipulating anything. It's mostly in the fingertips, so you have a very high concentration of Meissner corpuscles, or fine touch, here. As you go to regions of the body that are not responsible for, say, gripping anything, these are spread further apart, and your sensation in those areas are far less than in your fingertips. Merkel's discs are pressure receptors, which pressure receptors, I want to say, are called baroreceptors. But anyhow, Merkel's discs are going to tell your brain when you have a certain amount of pressure being applied to that area, especially if it's a constant pressure. In the epidermis, we also have our pain receptors. I mean, that's pretty much it. They receive signals of pain. And then, of course, transmit it to the brain. And then you have these hair receptors that are going to report the movement of hair back to the brain. That's it for that one. So the hair receptors are going to be in the dermis. And then let's talk about one more structure that's in the dermis. This is the Pacinian corpuscle. The Pacinian corpuscles, as I mentioned, are in the dermis. These are also a mechanoreceptor, but this time, instead of fine touch, think about they're much deeper, and so they're not going to be able to tell you information about the fine things that you're grasping. Instead, Pacinian corpuscles are going to be responsible for vibrations that are occurring as well as pressure. Okay? And that's all we're going to cover there. So let's move on. Oh, I forgot. By the way, throughout this video, I decided to add in little bits here, so that way, if you are not able to do these things, you're going to want to go back, okay? Because this is what this section of your video is going to make you require doing those 2 assignments. So you're going to need to be able to make a connection from the lacrimal gland all the way to the nasal cavity, and then distinguish between Meissner corpuscles and Pacinian corpuscles, okay? A couple similarities, a couple differences. All right, let's talk about hearing and equilibrium. First off, we've got 3 regions of the ear: external, middle, and inner. Sorry, I know I'm jumping around, but I just think it makes more sense. The external and middle ear are solely for hearing. The inner ear, when we get to that, is going to share hearing, and equilibrium responsibilities. All right. The external ear, not a whole lot to go over here. The part of your ear on the external, kind of like the funnel shape that is going to help direct sound waves into the ear, is called the pinna. The lower part is the lobe. This is also, the earlobe is technically part of the pinna. And then we have the external auditory canal. If you recall, in the skull, we had the external acoustic meatus, right? So we need a way for the sound waves and the auditory nerves to get into our brain. So this is essentially where your external auditory canal is. You are outside of the external acoustic meatus. Right, so this is a tunnel essentially that is going to bring in the sound waves, and you're going to hit this structure here called the tympanic membrane, which is your eardrum. Tympanic, like timpani, drum. Okay. Sound waves are going to bounce on this. It's going to then cause vibration in these ossicles, which are very small bones. We'll get into those in the next image. And then we also have the auditory tube. We're going to get to these in just a bit. All right, so let's just focus on the middle. As I said, here's the external portion of the ear. You have the pinna and the auditory canal. We are now picking up from the tympanic membrane or the eardrum and moving inward. Okay, so only these shaded parts are part of the middle ear. This portion in the background, that's kind of like a white outline, this is the inner ear. So we're not focusing on this white outline portion. Right now we're working on the stripy portion. So you have sound waves enter in. They hit the tympanic membrane, and they're going to hit this first bone here called the malleus. Malleus means hammer, because in some angles that's what it looks like. Not in this angle. From there, the malleus is then connected to the incus, which means anvil. It continues to send that vibration through to the stapes, and the stapes then connects to the oval window. We're going to talk about the oval window in just a bit. In other words, we're just kind of transferring vibrations. You hit the drum, the vibration continues through the malleus to the incus to the stapes. These are the three ossicles. These are the smallest bones in your body. And then the stapes is going to connect with the oval window so that we can connect our middle ear to our inner ear. Two more structures, though, that I want to chat about real quick. We have our tympanic cavity and our auditory tube or eustachian tube. These areas have a lot to do with the pressure in your ears. When it has to do with your ear popping. So you have fluid in your inner ear, but you have air in your middle. And when you have levels or changes in altitude, or even if you have pressure caused by inflammation or illness, the air pressure in that tympanic cavity can build up. And so in order to release that, we need to open the eustachian tube. And we do that by moving our jaw. Excuse me. Dustin, do you hear her? Sorry, Sawyer's not very happy right now. So you open your jaw, it's going to help open that eustachian tube, and that's when you hear a pop in the ear. That's the release of pressure. okay? So that eustachian tube is going to help maintain your inner ear, your middle ear pressure. Sorry, I can't focus because she's crying. All right. Final section of the ear, let's talk about the inner ear. Giving you a little bit of background again, the stapes is in the middle ear and it's going to connect at the oval window. The oval window is essentially the connection between our middle and inner ears. Okay. Now you have these semicircular ducts. These are not related to hearing. This is where our equilibrium comes in. The 3 ducts are named for the direction that they move. So we have the anterior, posterior, and lateral ducts. And then you also have these vestibules on the right of this diagram. The utricle is superior, the saccule is inferior. So these semicircular ducts with the vestibule is what's going to influence our balance, our equilibrium. Okay. The utricle is going to be horizontal movement. So it's sensing movement in this plane. Or even if you're just sitting still. The saccule is going to be vertical sensation. And then finally, the semicircular ducts are going to be rotation. We have fluid in all of these structures that is going to push against these hair receptors that we have. And so the fluid movement is what tells our brain, oh, well, the fluid in this duct is moving in this direction, so that means I'm rotating like this. Okay, so you know where your body is as it's rotating. We'll get into that a little bit more into the second. As for hearing, I mentioned that the oval window is where we have the connection between the stapes and the inner ear. But here we have the round window and the cochlea. Now, hang on, I made a note that I wanted to share. Did I make a note? Oh, the round window, because as I mentioned, we have fluid in here. The fluid is similar to cerebrospinal fluid. But anyhow, this round window is going to allow fluid movement. Because there's fluid in here, the vibrations that are traveling through the stapes to the oval window can then travel through the fluid in this area and into the cochlea. The cochlea is where our auditory receptors are going to then interpret those waves into neural signals. So that's how we get the message from sound wave to actually being able to integrate in the brain. Okay. I'm sorry if I'm all over the place. And so let's cover a little bit more about balance and then we'll call it quits on the ear. All right. So as I mentioned in the inner ear, let's see if I can move this. In the inner ear, you have the semicircular canals and the vestibules that are the saccules and the utricle. With the saccule and utricle, you don't have to move for those to understand your balance. So for example, if you're standing still, if you're sitting still, you can still maintain your position. Semicircular canals, however, are going to have fluid movement through them as you rotate, and at the end you have this ampullae, or ampulla if it's singular. And in the ampulla, you have this guy right here, which is called a macule. And a macule is a collection of hair cells. What happens is, as there's rotation, the fluid in the ear is going to push the hairs over so that your body knows which direction it's rotating or which direction it's moving. And that's about as far as we're going to get into that. Okay, so the movement of these hairs, depending on the direction that it's moving and the intensity of it depolarizing, is going to allow you to interpret the movement. One quick comment that I think is kind of interesting, for anybody that gets car sick or motion sickness, what's going on there, so when your body senses movement, so for example, your vestibules, if you are riding in the car and you are, you're the passenger, you're moving forward, the utricle is sensing horizontal movement, okay? You are moving in the car. It senses that. So that means your point of view should also be moving, right? Your eyes have these movements to adjust, focus. However, even though you're feeling your utricle depolarizing, if you're, say, reading a book, your eye does not have a movement that corresponds with, say, driving. I hope I'm making sense. Okay? So your eye is suddenly stationary when your brain's saying, I'm moving. I should be watching the horizon right now. And it makes you feel nauseous because suddenly your body's confused because your eyes are thinking you're staying still while your body thinks it's moving, which is exactly what's happening, but it makes you feel sick because you have these conflicting responses going on. All right, from that bit of information, you should be able to describe the pathway of sound through the ear. Okay, so going from pinna all the way to the cochlea. Describe the physiology of equilibrium. So what is the functions of the vestibules and the semicircular canals? And then I want you to look into vertigo. Very interesting. The test for vertigo actually has to do with the eye movements that occur when you are in motion, but the person is stationary. So I want you to look up what's going on with vertigo. What kind of scenario is happening in the inner ear that is causing that? I will tell you now, when you are researching, you're going to learn that inside the fluid in our ears, we actually have crystals that are like calcium deposits that normally float through in the area, and they just help with the motion and movement. However, with vertigo, there's a bit of a issue going on with those. So don't be surprised when you see mention of otoliths. Those are the little crystals. Okay. Let's talk about gustation. Sorry guys, we're just trying to power through here. All right, so taste. Why are you doing this? Okay. Is also known as gustation. A couple of structures are in this image. First off, you have the epiglottis. We're going to talk much more about this in the respiratory unit. The epiglottis essentially functions to direct food down the esophagus, whereas it then prevents food from entering the larynx In other words, you don't want food entering your respiratory system. In this image, you can see 2 sets of tonsils. You actually have 3, but the third set, the adenoids, are up in the nasopharyngeal cavity, which is why the adenoids are also called nasopharyngeal tonsils. Your palatine tonsils are the ones that are on the sides of your mouth and the roof of your mouth. The lingual tonsils are in the bottom with your tongue. You also have different types of projections on your tongue. You have vallet papillae. These are also called circumvallet papillae. We have fungiform papillae and filiform. We're going to talk about these 3 types of papillae in just a second. Side note, if you've had your tonsils removed, you most likely had your palatine tonsils removed and your adenoids. Your tonsils are part of your immune response. They help trap bacteria, viruses, things like that. However, some individuals have overactive tonsils, which results in swelling. So normally when you have a cold, they get swollen because they are capturing the bacteria. However, it can get to a point where it makes it difficult to swallow or even breathe, and so it's recommended that they are removed. So let's talk about the different papillae. Papillae just means round projection, and you have 3 types of papillae on your tongue. It's referring to this whole structure here. This is the circumvallet papillae or vallet papillae. You have about 8 to 12 of these on your tongue. They are towards the back, and they all have a taste bud area right here. If you can see that, it's kind of in this fold. These vallet papillae are much larger. They're in the back, and it's proposed that these have to do with tasting bitter and, I guess, gross tastes. And they're in the back of your throat so that it can initiate the gag reflex. So typically if you are ingesting a food that's, say, toxic or spoiled, it tastes bad, it might taste bitter. A lot of, I guess, poisonous plants, if you ingest them, they have bitter taste, and it triggers the gag reflex as a way to help protect your body. In other words, they're saying, this is bad for you, it tastes atrocious, you need to get rid of it, and it's going to force you to gag. Your normal taste, so sweet, salty, sour, all that good stuff, is going to get picked up in the fungiform papillae. They're only named this because the person who discovered them thought they looked like little mushrooms. I think the vallet ones look like that more than they do. But the fungiforms actually have multiple taste buds surrounding them. And so that's why you're going to be able to taste so many different types of chemicals with them. I mean, they're chemoreceptors. Finally, you have these filiform papillae. These are just texture projections. With your filiform, this is kind of like your touch receptors for your tongue. Touch, temperature. Yep. Okay. All right. So filiforms have nothing to do with taste. They just have to do with touch. It's the circumvallet and fungiform that have to do with taste. And let's talk about how taste exactly works. Here's a taste bud. And there's all kinds of cells here that have these afferent connections. You have a pore, and then like I said, your afferent connections, your nerve fibers. As you begin to chew or as food settles, saliva begins to break down the chemicals that are in that food. And the dissolving of chemicals will allow the chemicals to diffuse through the taste bud so that the chemical diffusion can trigger an impulse to the afferent nerve fibers. So depending on which cells are depolarized, the intensity of depolarization, it's going to affect your taste. Because these are chemoreceptors that required the dissolving of chemicals or the diffusion of chemicals through your saliva, this is why it's difficult to taste when you have a dry mouth. Because you can no longer dissolve those chemicals and they can no longer diffuse into the taste pore. And I think that's it for taste. So let's get into olfaction, which is smell. If you recall with our brain dissection, you should have seen the olfactory bulbs. They were kind of like little antennas in the anterior, inferior portion of the brain. Off of the olfactory bulbs, you have these olfactory filaments. In other words, nerve fibers. Okay? You have these olfactory nerve fibers that are going to cross through the skull. We're going to show where that happens in just a second. And it's going to innervate or mingle in with olfactory epithelium. In other words, the membrane tissue. And that olfactory epithelium is what's lining your nasal cavity. When you have a scent come into your nasal cavity, this is very similar to the taste pore. You have mucus all along this lining. The chemoreceptors that are these filaments are going to be depolarized by the chemicals in the scent that are diffusing through the epithelium. Let's take another look at this because I think I'm just babbling. All right. So here's our olfactory bulb, right? This is our brain, part of our brain. It's a little antenna on the bottom of our brain. And we know that our brain sits in the skull, right? And if you recall when we did the skull, you had the sella turcica, which was where the pituitary gland sat, and then anterior to that, you had the cribriform plate that was kind of like polka dotted. I really wish I had my skull to show you, but I don't. I'm sorry. You can also look this up, of course. But the cribriform plate has all these pores in the bone. Those pores are where the olfactory filaments are going to travel through. Okay, so I don't know why this image isn't showing it, but here's where your filaments or your nerve fibers are traveling through. It's traveling through the cribriform plate in the skull. From there, it meets up with the olfactory epithelium, and that's the tissue that lines your nasal cavity. And that's going to consist of olfactory cells, smell cells, supporting neural cells, and olfactory hairs. Okay, and so this is where you have the mucus that when you breathe in, that mucus is going to capture the chemicals within the air and it's going to diffuse into these olfactory cells. The concentration is going to then cause depolarization of the olfactory filaments. The olfactory filaments are going to take that depolarization through the cribriform plate and to the olfactory bulb. And you can smell. All right? That's it for senses. So now, from that section of the video, you should be able to distinguish between the different types of papillae. Talk to me about the physiology of the taste bud. and explain essentially the layers or the steps of olfaction. So once you go from inhalation of an odor or chemical, how does it get from the air to the olfactory bulb so that we can integrate in the brain? Unfortunately, we can't do this activity. We would have been doing a competition with the, oh gosh, what are they called? Bean Boozled. Bean Boozled? Something like that. Because it actually works that if you inhibit your smell, you lose your sense of taste. And so we kind of would do a competition where you would have to essentially convince your partner whether or not you had a good tasting bean, whether it was good or not. And the way you can do that is through inhibiting your sense of smell, eat it, and then once you release, you can have a hint of the taste. So hopefully you could suppress your reaction for your partner. Because we can't do that, sad, I want you to do a little bit of research as to why that is. Why is it that we lose our sense of taste when our smell is inhibited? This is one of the things that you might notice when you get sick. Once your nose is stuffed and you can no longer smell, you might not be able to taste food very well. Okay? So let's go ahead and look. We've just got this overview here. So again, this is nothing new from any of the other slides. I want a connection from the lacrimal gland to the nasal cavity regarding anatomy. You're going to distinguish between Meissner and Pacinian corpuscles. Describe the pathway of sound traveling through the ear. This includes the external, middle, and inner ear. The physiology of equilibrium. What are the roles of the semicircular ducts and the different vestibules? I want you to look up what's the relationship between inner ear structures and vertigo. And again, when you're researching this, you're going to see them, your resources might talk about otoliths, and these are the crystals that are floating in the inner ear fluid. Again, distinguish between the papillae, the physiology of the taste bud, layers of olfaction, and why do we lose our sense of taste when our sense of smell is inhibited. As always, any research that you do, make sure you're including the resource. So at the end of your response, I'm not expecting APA for this or anything. If you can just say sources, ... and then provide me with the links to the websites that you're using, that would be great. I do appreciate when people are using quotations. Just be wary of how many you're using, because I still need the response to be your own original thought. If you're using quotations, those should be supporting your response. The quotations are not your response on their own. All right. As always, if you have any questions, make sure that you send me an email, contact me on Remind, or chat on It's Learning. We will have our weekly Teams meeting on Friday at 1 o'clock in case you have any questions. Bye.